Dear students, welcome to the course on mechanics of machining. This is 9th lecture. Today I will be talking about various other models of finding out the cutting forces in orthogonal machining. Till now we have discussed about Merchant's force analysis. He used single shear plane model. Ernst and Merchant together they published many papers, and Merchant also has published papers. So that is very popularly known as single shear plane model. Even I discussed about slip line analysis of Lee and Schaffer. Lee and Schaffer slip line solution also assumes a type of single shear plane, but although it is a slip line, but here we established this type of relation. There was a phi and then there was a slip line. This is considered as a slip line, and then there was a free surface. This was the tool, like that, and it is and after that he deduced the relation between the shear angle, rake angle and friction angle, which is different from Merchant's relation, and therefore the power etc. will also be different. But nevertheless, it is also assuming a existence of a shear plane like this. Then after that there are other models. We will discuss those things today in the lecture, and also we may give some exposure to the finite element method of finding out the cutting forces. So if we go to this one, that what is the main objective of metal cutting mechanics? The main objective is to determine the cutting force. Passive forces means which do not participate, like thrust force, which doesn't produce any power, and cutting power through analyzing the thermomechanical processes involved in the cutting process. So we have to do temperature analysis also, and we have to do stress analysis also. Till now we are only talking about stress analysis. We are yet not talking about the temperature analysis. Then we can say totally there can be 4 type of models. One is the analytical one, like Merchant's analysis. You can say it provides analytical model. It will usually give a closed form solution. Even Lee-Schaffer's model also gives closed form solution. Then there can be experimental or empirical model, which is based on the number of experiments. We conduct number of experiments and we try to set one relation. In the last lecture also I wrote something like this: cutting force is equal to K times feed to the power A and D to the power B. Here F is the feed and D is the depth of cut. So such type of relations can be fitted by conducting number of experiments and then finding out some relation. Then third type of model is mechanistic model. In the mechanistic model, we actually it is some type of, we can say, semi analytical model, semi experimental model. How do we do that? Suppose we obtain some type of relation that it should be like this, but the coefficients of that relation we can obtain by experiments. Means there is some physical basis, but it is not completely only by physics of that. So that type of model is called mechanistic model. Okay, like I can say with my physical reasoning that the cutting force should be proportional to the chip cross sectional area. So maybe it is proportional to F into D. But what is that proportionality constant? That can come by some other methods. And then if there is even number of cutting edges are there, or the cutting edge is in helical form, that type of thing also can be done by transformation process. We can find out the aggregate effect. That means at one location I can make a simple model, orthogonal cutting, and then after that I can keep on adding these small contributions and properly transform to account for the angle of the helix. Then the fourth type of model is the numerical model. In that we use some governing equations which govern the behavior of metal cutting. So those governing equations we can take like continuity equation, equilibrium equations. These equations have to be solved not analytically but by means of numerical methods. For example, we can use finite difference method or we can use finite element method and other type of techniques also. So such type of methods are called numerical models. Now first let me discuss again another strip line field solution that is given by Auxerre. Earlier that Palmer and Auxerre in 1959 they discussed this model and then Auxerre further developed it. That model I am going to discuss. It is also strip line field solution, but here they are assuming a shear zone actually, not a type of identified shear plane, but there is a complete zone here. So they conducted a lot of experiments and published a paper in 1959. Those experiments were of course conducted at low speed machining, and they recorded the paths of individual grains on the side surface of the workpiece using a cinema film camera. By that they recorded that how the grains are deforming, and then they concluded that there is a thin shear zone in machining. So Auxerre assumed the narrow deformation zone bound by parallel strip lines inclined at an angle phi to the direction of cutting. So he assumed that although this zone is like this, but to a first approximation I can consider it like a zone bounded between two parallel strip lines, and these are inclined at an angle phi. So it is just like a shear plane angle. So here this SR is one bound and maybe TU is another one. In fact, they provided some small curvature near S, so that it ensures that the strip line meets at angle of 45 degree at free surface. Okay, so at this one. So there is a small curvature type of thing. Why it should meet at angle of 45 degree at the free surface? Because free surface will be divided of any stress and it will be one of the principal stress plane, one of the principal plane. So the shear plane must make 45 degree angle from this. So since the strip line is the gives the direction of maximum shear stress, so therefore it must meet at the free surface at 45 degree angle. So that's why they provided some small tilting type of thing, but that is very small. And in this figure I have not depicted, I have depicted two straight lines. So maybe that this side total zone is H, and this may be something like K times H, and this may be 1 minus K times H, like that. And so this type of assumption they took, and then after that I am not going to describe the complete details about that, but they considered the strain hardening also. Usually the strip line method is used for plane strain problems and material is rigid plastic. There is no hardening, but it can be incorporated. It makes the analysis cumbersome. So they incorporated the hardening also, and relations are like that: P plus 2K psi, and this portion, if K is constant throughout, then this portion will be 0 and you will get usual Hanke's equation. So, but these equations are given here. That one equation is constant along alpha line, another is constant along beta line. Now, if you neglect the work hardening term along the strip line, that means across the strip line there is work hardening, there is no doubt about that. Here there is a, that means if you go from SR to TU, naturally material will get strain hardened, but assumption is that along SR there is no hardening. If we assume that, then you will get this type of relation: P plus 2K psi is equal to del K by, because del K by del S alpha here will be 0. So you will get this type of relation that will be constant along alpha line. P plus 2k psi plus integral del k dou k by dou s beta into ds alpha equal to constant, and then you will get similarly one relation along beta line. So these relations they obtained, and other procedure they followed in the similar way, and then Auxerre and Hayton in 1963 they considered this also. You know, the shear stress is not uniform on the surface. In fact, there is a sticking zone. This is sticking zone from, this is the tool cutting edge point A, and from A to some distance there is a sticking zone or sticking region. So that is, in this portion shear stress remains constant, and that is K, and after that there is a sliding region in which you can say Coulomb's law holds good. And then, as I have shown in the last class, that the normal stress is parabolic type of thing. Here you get the maximum normal stress and gradually it decreases, but they assume that, let us consider that it is not parabolic, rather it is just a straight line variation is there. So if you parabolic means it would have come like this, but some error will be introduced. So they said let the normal stress be like that. And then based on all these things the analysis was done, and you get another type of relation, that is phi is equal to 50 degree minus 0.8 lambda minus alpha. And Auxerre's analysis also predicts a moment due to which chip curling takes place. Means he considered in that model that the forces will generally not pass through this point, rather the force may pass here, and this will create a moment. So that type of thing also has been done. Those details are available in the textbook, but we are not going to discuss that much. I am just providing you some exposure that such type of analysis is also available in the literature. Now another one approach that which is in fact a still very active approach, people are doing it, that is unified or generalized mechanics approach of, particularly Amerigo and co-workers, they propagated that scheme. In this, models for different machining operations could be unified into a modular computer application structure with generic cutting analysis and database. Suppose you keep lot of database. Suppose I keep the database for, let us say, the turning process. If I have kept the database for turning process, how, when depth of cut was this and feed was this, then this was the force, then same type of information can be used for modeling of the milling. If we understand the basic concept, only thing that there may be two cutters simultaneously cutting, so you take that effect into account. There may be a helical type of cutter tooth, so you take that helix angle into account. That means you have to integrate small segments. Helical tooth can be considered as a series of the tooth which are having different types of angles. They are arranged a little bit staggered, that's what. So, but basic database can be common. So that's why we say that generic cutting analysis and database. So in this we consider cutting force component due to shearing and friction. Then we consider edge force components due to rubbing and ploughing in the basic concept. And then cutting force components are proportional to uncut chip area. We say cutting force components, they are proportional to uncut chip area. So and edge force components are proportional to uncut chip width, because edge cutting means this is a tool, and suppose I make a tool, this tool is moving here. So here this is the cutting edge which is going perpendicular to the screen. That edge is there, no? So this edge will do cutting and it is having some width, so that other rubbing force may be proportional to chip width, okay, rubbing force also. So this Fc is equal to KCC T1W, that is the first part, because chip load due to shearing and friction will be proportional to T1 and W. So KCC T1 into W. W is the width of the uncut chip width and T1 is the uncut chip thickness, plus KCC into W. We can write it KCC into A. A is the uncut chip cross-sectional area, and this can be also called a chip load. People call it as a chip load. That means this is the total chip load. So, and this one is KECW, edge cutting force. Then thrust force component can also be written in the similar way. Ft is equal to KCT1W plus KETW, KCTA plus KETW. Okay, this can be written for any general process, any machining process you can write. Now here, suppose you want to do that simple orthogonal machining, in that you already have that relation from Merchant's analysis, which was given in this form. Fc is equal to Wt1 tau s shear strength, and then this was cos lambda minus alpha, or that type of things, and Ft also we derived that expression. So if we consider Wt1 as the chip load, then it is clear that this another portion should be coefficient. So that must be KCC. So like that I have found that KCC is also there. KCC is a function of now alpha, and it is a function of lambda and all that type of thing. And KCT is also a function of alpha, lambda and phi, like that. So this one, so like that you can have the data and you can calculate. But then around the same time, Shivji Kapoor and that group, they developed the mechanistic models. Mechanistic model and unified generalized mechanics approach, more or less they are similar. They developed around the same time, and a lot of work has been done. Here also they assume that forces are proportional to uncut chip area, and uncut chip area is also called chip load. Then transformational relations can be used for multi-point cutting. So for multi-point cutting, we can use the transformation type of relation. Suppose my cutting edge is, one cutting edge may be here, but suppose this is some type of end mill, and if you know that at this point how much the force is causing this cutting edge, then on the next layer also you can consider that this is also a cutting edge, but angles will be slightly different. Like that you can find out aggregated effect. It is like this, that you can have aggregate effect of all the type of forces, and then you get mechanistic model approach. So this lot of papers are there on this topic. Each one has developed some mechanistic model for one type of process using the transformational relations. These details you can get in other papers. Here we will not be discussing much about individual papers in detail. So we move to another approach, that is energy approach of Astakhoa. Astakhoa has proposed, Astakhoa has written lot of papers and books on metal cutting. In fact, earlier also I discussed one paper of Astakhoa in which he criticized single shear plane model and Merchant's analysis. So in one of his book he has described the energy approach, and he says the forces etc. can be found by energy approach. Here we consider that total power comprises the following: power spent on the plastic deformation of the layer being removed, then power spent on the tool work interface, then power spent on the tool, this is plastic deformation of the layer removed, then power spent on the chip work, no, this is tool chip interface, this is tool is okay, and this tool chip interface. And another power is the power spent on the tool and work interface, because tool is like this. So on it has got two surfaces, main surfaces, that is rake. On this the chip is moving. So tool and chip are interacting, and similarly that here tool and work are interacting. So that power also has to be considered. Then power is spent in the formation of new surfaces. That power also, he said, should be considered. Like you saw that in Atkins analysis also, that type of power was considered. So that is the approach of Ashtakhon. And then he also pointed out once the interesting observation about inadequacy of single shear plane model. For example, machining of medium carbon steel, that is AISI 1045, which has about 0.4% carbon. In that ultimate tensile strength is 655 megapascal and yield strength is 375 megapascal. Another steel is stainless steel, that is AISI 316L. Its ultimate tensile strength is 5.7 megapascal and yield strength is 218 megapascal. So both these strengths are lower. It should give that lower cutting force, but actually this gave higher cutting force. In fact, this gave higher cutting force. We expect that it should give lower, but it gave higher. And this actually, which has more ultimate tensile strength, it gives lower. So why it is so? That means Ashtakhon argued that this may be due to larger strain encountered in this material. Okay, that lateral material, that means in stainless steel part, there may be this one. There may be lot of redundant deformation. There may be lot of unwanted deformation. Suppose I want to cut some material and this chip is there, this portion has been cut. Now we require the energy in cutting, but during the process the chip thickens and you know it shortens also. So this I am doing unnecessary. Chip thickening is not of any use, but it happens, but it takes energy. So it is a type of, we can say it is redundant energy. If another person can do the simple cutting operation same way, but energy is not required, that means lot of deformation of the chip is not there, in that case his energy will be smaller. So stress is one thing, but the strain is another thing. Stress into strain, they give the energy, product of stress and strain. So this may be due to that. So you have to consider that strain effect also. Now how do we calculate power for plastic deformation? Why I am giving one illustration. Let us consider Holloman relation of strain hardening. So here sigma EQ will be K times epsilon EQ into N. N is the exponent and K is the strength coefficient. Now energy density in deforming up to strain epsilon F. Suppose I know that this is my fracture strain, that means this will be the strain for causing the fracture. Okay, so then we can integrate 0 to epsilon F, K epsilon P EQ into D epsilon EQ. Stress into strain give me energy density, that means energy per unit volume. So if I take product of that stress is this whole quantity, that means epsilon EQ, and multiplied by D epsilon EQ, that will give small energy. But if I integrate between 0 to epsilon F, I will get total measure of the energy. So if I integrate, I get this type of expression, K epsilon F n plus 1 divided by n plus 1. So power is equal to total energy in unit time. So if I multiply this energy per unit volume by volume rate of metal removal, that is T1W into V, V is the cutting speed, then I get the total power. So we got this type of expression. Now how do we find out epsilon F? If I can measure the chip thickness, then I get the idea about that strain, that means assuming that it is a plane strain process. So you get the thickness direction strain and the length direction strain. Of course, both these strains will be equal and opposite because the total volume has to be constant. So one is that suppose chip has become T1 to T2. So you get that ln T2 by T1. And similarly in other case you get ln T1 by T2 because length na L2 by L1, but L2 by L1 is nothing but T1 by T2, okay, because you know that L1 T1 is equal to L2 T2. So these are the logarithmic strain measures, and of course ln T1 T2 is nothing but minus ln T2 by T1. So I can find out now the equivalent strain. Equivalent strain is what? Square root of 2 by 3, and then I square all the non-zero components of the strains and add them. So there are only two non-zero components of the strain in this axis system. One is the chip is thickening, and then chip is also getting shortened. So I took ln T2 by T1 square plus ln T1 by T2 square, and then I took the square root of this. We get 2 by under root 3 ln T2 by T1, and ln T2 by T1 is nothing but the chip compression ratio. It is more than 1, and we say 2 by under root 3 ln zeta. Hence the power for plastic deformation becomes, here 2 by under root 3 is nothing but 1.15. So we substitute in this expression, and it becomes K 1.15 ln zeta divided by n plus 1 to the power n plus 1 and T1 Wv, and this becomes, this I can, instead of W I can write F, and instead of T1 I can write D depth of cut, and I get this type of expression. So this way I can calculate the power for plastic deformation. Now we can find out power due to friction at tool chip interface, tool and chip. So chip is riding on the tool. So here we find out P friction is equal to M. M is a friction factor. Its maximum value can be 1. So M times sigma y by root 3, that gives a constant shear stress, and LC is the chip length, then W chip is the width, and then we say that here, so LC into W chip, that will give you that force, shear force, and then V multiply by V, in fact VC, because the chip is moving with the velocity VC, but VC is equal to nothing but V by chip compression ratio tau. So you get this type of expression. M has to be of course found out by experiments, because M is the friction factor. If there is some lubrication, M will be small. If there is no lubrication, M will be big, like that. And then LC is the chip contact length. That means how much is the length of the contact, because chip separates. There is a tool, and on this tool the chip is moving. Suppose my chip is going like this. So contact length is up to this. This he gave empirical type of expression, and this LC is equal to T1 multiplied by chip compression ratio to the power 1.5. So this expression can be used, and you can get idea about the friction power. So two powers we have obtained. Then power due to friction at tool work interface can be found. P at the flank can be friction force at the flank multiplied by V. So this portion also you can find out. You can consider that this force to be proportional to the cutting edge width, and it may be function of nose radius. Those type of things can be taken into account. And then other things also, chip, that power is spent on the separation of new surfaces, that can also be considered, and all the energies can be combined. You get the total energy, then divide it by cutting speed V, and then you get cutting force. So this way you can find out the cutting forces. So all these analyses are there. There are many other methods also, like one is the upper bound method, in which we find out upper bound of the cutting force, that how much will be the maximum cutting force, like that. And there are many slip line field solutions. So all these methods are not able to match the numerical methods like finite element modeling. Although finite element modeling of machining process is also difficult, but nowadays finite element modeling has been incorporated in many commercial packages like Deform and in Abacus etc. also you can do finite element modeling by doing some work from your own side by writing some small codes etc. So I will give some exposure about finite element modeling, because nowadays you can get even ready-made codes, and in that you use them as a black box, but you must also know that what is going inside. So very briefly I will tell about the finite element modeling, at least that what are the equations actually which are being solved by finite element model. So first some introduction, that machining processes are difficult to model for various reasons. One is that unlike metal forming processes where almost the whole workpiece gets plastically deformed, in machining processes the plastic deformation is localized near the cutting edge. So you have to consider only the localized one, so that local thing has lot of effect. If the local layer is very hard, it will have significant effect. In metal forming, whole thing you are analyzing, suppose local layer you are not able to model properly, or you have taken the average property, that will do. But average property type of thing in machining will not work. So we need to analyze only a small region of the workpiece around the cutting edge, that is called the cutting zone. As a result, the selection of the domain dimensions and the appropriate boundary conditions becomes a difficult task. And further, even at a moderate cutting speed, the strain rates are quite high, although it is also uncertain that how high it is really. But many people believe that it is almost of the order of 10 to the power 4 per second, and temperature rise is also quite large. As a result, the viscoplasticity and temperature softening effects become more important compared to strain hardening. We consider that flow stress is also a function of strain rate. So material properties associated with these two effects should be known for a range of strain rates and temperatures occurring in typical machining processes. These properties are not readily available. Additionally, to incorporate the temperature rise in the analysis, one needs to solve the heat transfer equation governing the temperature field in conjunction with the usual three equations governing the deformation field. So you get three equilibrium equations, those have to be solved. In addition, you have to solve the heat transfer equations, but heat transfer equations you can solve by finite element, or you can solve by other methods also, analytical methods also. So for plastic deformation, these equations are coupled and hence difficult to solve. So as such they are coupled, because if temperature affects this one, stresses and stresses affect the temperature, but we can often decouple them, and we first estimate the average temperature in the cutting zone either experimentally or by some simple analytical methods, and then we solve the governing equations of the deformation field by evaluating the material properties at the estimated average temperature of the cutting zone, that means average way I have found. And then two methods, this process can be repeated after you do that analysis, then again you can find out the temperature, and again you can do this one. So you can do in a sequential manner also. Here two methods exist for analyzing the machining processes. In the first method, it is assumed that the chip formation is continuous and its shape is known a priori. So chip is known in advance. So process can be analyzed as a steady state process, that material is moving through that control volume, and this method is called the Eulerian method, control volume method. Another, so in this method the chip separation criteria is not required, and in the second method the process is analyzed from the beginning to the steady state chip formation. In the second method, process is analyzed from the beginning to the steady state chip formation. We follow the material, though this is called the updated Lagrangian formulation. In this method, a chip separation criteria is required to predict the chip geometry, that how when the chip will separate, that type of thing has to be incorporated. In this, we find out the position etc. and stresses of one time step, by taking the reference as the previous time step. That is why it is called updated Lagrangian formulation. But earlier people mostly used Eulerian approach, because Eulerian approach will take comparatively less amount of time, although you get more detailed information if you do Lagrangian approach. So main objective of many of these studies was to predict the temperature distribution, and therefore the determination of deformation and stress fields was only an intermediate steps, and these studies considered the machine material as rigid plastic. So if you want to find out even the temperature distribution, still you have to find out stresses, or if you want to find out stresses, naturally you must know the temperatures. But later application of Eulerian formulation to machining process included viscoplastic effects, and all of these applications have considered only orthogonal machining. The first finite element study of the machining process using an updated Lagrangian formulation was made by Strenkorsky and Carroll. This was for orthogonal machining, and they used a critical value of the equivalent plastic strain to model the separation of a chip. Suppose you keep on analyzing and finding out the strain, and when that particular strain becomes more than a critical value, then you can say that the chip separation is taking place. Later on, several researchers used updated Lagrangian formulation for analyzing 2 and 3 dimensional machining processes. Most of these studies have used FEM package. Abacus is one FEM package, Mark is another one, Deform is another one. Deform is very usual, friendly, it is used for metal forming and metal cutting studies, and in the other packages you have to work something, but they may have more flexibility. Criteria used for chip separation has been based on controlled crack propagation or some geometric consideration, and they have used remeshing technique to simulate the chip formation. Suppose when deformation occurs, then again you make the mesh again, because if suppose I make a mesh here in this region like this, and then suppose it has deformed, then naturally you have to make a different type of mesh. That type of thing is also done in those packages. And let us discuss finite element modeling of orthogonal machining process. We assume that the problem is decoupled, that means we can estimate some temperature, and after that we can do simply the stress analysis, and we assume that the elastic deformation is small, so neglect any elasticity, and viscoplasticity and temperature effects are more dominant compared to the strain hardening effect. So we don't consider strain hardening, but rather we consider viscoplasticity and temperature effect. And to keep things simple, we assume that the material exhibits no hardening but only viscoplasticity. Thus we assume the material to be rigid viscoplastic. Further, the temperature softening is accounted for by evaluating the material properties at an average temperature occurring in the cutting zone. Additionally, we analyze the process when it has reached a steady state value, steady state condition, then the transient term in the equation of motion vanishes. So transient term is not there, and we further assume that the body forces are negligible. What are the body forces? Like such as the gravity force, which is distributed in the body. Those type of forces are neglected. Interaction of the forces is only through the surfaces by external agency. So here we choose a small region of the workpiece around the cutting edge called the cutting zone as the control volume, that is the domain of the problem. Then to make the problem two-dimensional, we assume that the width of the cut is large compared to the dimensions of the cutting zone, so that we can say it is more or less a plane strain type of situation. The domain along with the coordinate system is shown in the next figure, and it is a region in the cross-sectional plane of the workpiece perpendicular to the cutting edge. Now here this one is this type of thing. We make this type of domain. This is uncut material, and then this is the domain. So here point is the projection of the cutting edge, this point is the cutting edge, then z axis is along the cutting edge or the width of the cut. That means in this screen only you are seeing x axis and y, z is perpendicular to the screen, and then boundaries AB and EF are actually circular, but we have assumed AB and EF. This one AB and maybe that this is EF, these are free surfaces, they may be circular because some bulging will take place here, but we assume that they are straight line. And now angle alpha is equal to the rake angle of the cutting tool. By now you very well know it is alpha, that means surface of the tool is inclined at an angle alpha with the vertical, and the distance h is called the tool chip contact length, and we use the following expression for h, f sin theta by this one. So this is the type of expression has been used. Earlier I told another expression by Astkhov. So this is these type of things you have to consider. So suppose they have taken only this type of relation, and in orthogonal machining the shear angle can be estimated by measuring the cutting ratio, and that is given here. Now here angle theta is actually, theta is the angle between the shear force and the resultant force, and F is the feed. So theta is the angle between the shear force on the shear plane and the resultant force on that plane. That can be easily obtained by Merchant circle, and it is given in this manner: Fc cos phi minus Ft sin phi divided by this one, and Fc is the cutting force and this is the thrust force, and by a dynamometer. So we can find out this force. Boundaries AH, HG, FG and CD are placed sufficiently away from the cutting edge projection E. So they have been put sufficiently away. So in this process, then we assume that boundaries AH, FG and CD are chosen parallel to the shear plane. So this way, so this AH and shear plane BE and CD are all parallel. So mesh generation will be easy, and here you can assume that at CD everywhere this velocity is VCH, there is uniformity here. Now for the decoupled problem of the rigid viscoplastic material with zero body force, the velocity field V, the strain rate field epsilon dot, the hydrostatic stress field P and the deviatoric stress field sigma dash in the control volume are governed by the following equation. We have strain rate velocity relation, then we have stress strain relation, then we have equation of motion and incompressibility constraint. Now these equations need to be expressed in the component form. Velocity vector has two non-zero components, and the strain rate and the deviatoric stress tensors have three non-zero independent components each. So what are these equations? Suppose we write strain rate velocity relation, we can write epsilon dot xx is equal to del vx, that means velocity in the x direction divided by del x. Epsilon dot yy, strain rate in y direction is this, and shear strain rate is given by this. That is one type of relation that has to be used, okay, because in FEM you will be then predicting what are the velocities at different nodes. And then there is a rigid viscoplastic deviatoric stress strain relations. So this is basically viscoplastic, that means we can say viscoplastic. So here if it is non-hardening, then we get this type of relation, that deviatoric stress. What is deviatoric stress component? That you subtract the hydrostatic part from the stress tensor, then you get deviatoric stress tensor, and then you have 2 eta 2 into epsilon dot xx, and here this is a proportionality factor eta 2, and this is given by eta 2 is equal to A times something strain, equivalent strain rate to the power m plus this portion, that sigma y by 3 epsilon dot eq, that anyway would have come, but this portion has come because of the viscoplastic effect. So that such type of relations of plasticity have been used here. And temperature softening is considered. Material constants are evaluated at the average temperature of the cutting zone. Then we write the equation of motion. Equation of motion are written like this. X momentum balance in x direction gives you this, and momentum balance in y direction gives this. But P is the hydrostatic pressure acting on that particular point, and this is deviatoric stress. And if we say that inertia effects are neglected, then this portion will go here, and in that case, now in this we consider incompressibility constraint also. So incompressibility constraint in the component form becomes epsilon dot xx plus epsilon dot yy equal to 0. That is incompressibility constraint. And then we consider boundary conditions. Note that since the problem is two-dimensional, only two boundary conditions are needed on each boundary instead of three. So whether a boundary condition is essential or natural is also indicated against each boundary condition. That means in FEM we have two type of boundary conditions. One is in terms of the primary variables, like our velocity and hydrostatic pressure are the primary variable. So we say suppose velocity is specified, that is called essential boundary condition. And if the derivative terms are used in the boundary, like suppose strain or stress is the derivative of the velocity, then we say that it is natural boundary condition. So at these boundaries AH, HG and FG, here we assume that the velocity vector has only x component at these boundaries. AH, HG, here only x component AH, and then you have got HG, then you have got FG. So here FG also only this one, and HG also, if we assume that it is only cutting like this, so we assume that it is only in x direction, that is VC, that. And then as we can assume that the velocity vector has x components. Now actually the velocity varies linearly from H to point A, that means from here to here, and from point G to point F. But since the distances are very small, we assume the velocity to be uniform. Okay. Let now VC be the specified cutting velocity, then the boundary conditions become Vx is equal to Vc and Vy is equal to 0. So that type of boundary condition we put at boundary CD, that means this boundary CD, this is that free boundary here. At this boundary, from the cutting edge, we assume that this boundary velocity vector is uniform over the whole boundary. So VCH is the chip velocity, and this VCH is equal to VC times R. And in this case, boundary conditions at the boundary CD becomes Vx is equal to Vch sin alpha, Vy is equal to Vch cos alpha. That means we have expressed that in terms of Vx and Vy, because ultimately at each node we will be having unknown variable like Vx, Vy and pressure. So we expressed in that way. That has to be done. And stress free boundaries AB, BC and EF, on these, because these are stress free surfaces AB, so we simply say that Tx is equal to 0, traction in x direction equal to 0 and Ty equal to 0. And now this one is, now we can of course take any other type of boundary conditions also, but we are generally taking free surface one. And now what about that boundary BC? BC, yes, BC is inclined here. Since the inclination of boundary BC with y axis is alpha, so we can write Vn, that means normal component across BC 0, so Vn equal to 0, but by trigonometry you have to transform Vn in terms of Vx and Vy, and you get V1 is equal to minus Vx cos alpha plus Vy sin alpha equal to 0. That is essential boundary condition. And then you get a natural boundary condition Ts equal to 0 because it is free surface. Ts means tangential stress is not there here, but that is expressed in this form, and they are expressed like this. Then at tool chip interface, velocity along the tool chip interface can be approximated by the following relation. This is a sort of empirical relation. This is given here, and then velocity keeps on increasing first, and then after that it becomes constant. This one, now note that this makes angle alpha with y axis, so we can again transform in Vx and Vy. Like that we do all these type of things, and then what do we do that? We take these equations. Suppose you have this equation epsilon dot xx, we have this one, we have this equation. Now we know that epsilon dot xx is what in terms of the velocity derivatives, and we integrate these equations, we multiply each equation by weight, some weight function Wp, Wx, Wy, and we say integrated thing is 0. That is the procedure which is followed in Galerkin finite element procedure. Okay, so I am just telling that this one is done, and then after that we obtain the derivative of these equations. That means we integrate these equations by part, because we observe that sometimes there is second derivative of velocity, some places there is a first derivative of the velocity. So if we integrate by part, then we can reduce sometimes the order of derivative. That procedure is done, and as a result you get this type of equation. I am not going to discuss that in detail, and then we have this type of relations, that of course you get these equations at the boundary sigma xx nx. That is actually a relation of Cauchy, that by which you get Tx traction Tx is equal to sigma xx nx. Nx is the x component of the normal direction, and in y this one. So these equations are there. If you have to just revise the basics of the solid mechanics, otherwise time being I am just telling you the basic concepts, so you can ignore if you don't really know. But here after that we get this type of, we represent everything in the matrix and vector form, so that it becomes easy to manipulate. So this is strain rate and this is this one, and after that we put all that type of data, and we take, there is some concepts of that suppose velocity at each node has two components, and it is interpolated type of thing, that we assume that velocity inside the element will be interpolation of the nodal velocities, and these interpolation functions are basically called shape functions. Suppose I have the velocity v1 here, suppose some velocity v1 and some velocity v2. So we can say v in the domain v is equal to n1 v1 plus n2 v2, where n1 and n2 are called shape function or interpolation function, and n1 may be the function of x, n2 may be function of x, so like that. So it is nothing but the interpolation function. I am mathematics you can study later on in detail. I am just telling you basic concepts, so that when you study the mathematics, then it will be easy for you to follow. So these shape functions, everything is expressed in terms of the shape functions, interpolation function, because in finite element we find out only the nodal velocities. But of course we can say that we know everything because we can interpolate them. So interpolation is upright, and then we put all these thing here. We obtain these type of relations, B times VE, and then this is B matrix, derivative matrix, means interpolation functions have to be differentiated, because you have to get strain rate from velocity, and then you substitute all these type of things, and then you get in the matrix form, you get nice type of expression. Finally you get that this type of thing, that Ke delta E, and this is this one. So but this requires a lot of integration inside, because you have to integrate. So integration is usually done by numerical method like Gauss quadrature, etc. And here you transform. That transformation is done how? That you transform from physical coordinate system to natural coordinate system. In natural coordinate system, any domain is getting transformed to -1 to 1 and -1 to 1. That means square domain here. That means transformation you can do, but in applying the Gauss quadrature, we generally try to make this type of domain xi and eta, and this is -1, -1, and this is +1, +1, and you get Jacobian, determinant of Jacobian. That is basically transformational relation. That means Jacobian can be defined like this. This type of thing we can put even the coordinates also. X position at any point is also interpolation of various nodal coordinates, and we put all that type of thing, and then after that you will get finally this type of equation, K delta is equal to F, and this will be algebraic system of equations. So we started with the differential equations, but finally we ended up with algebraic equations. But of course this K may be non-linear, that means K may be function of delta. In fact, in metal cutting process it is non-linear. So we are getting simultaneous, not the linear system of equations, but simultaneous non-linear system of equation. K is called the coefficient matrix. Sometimes in packages they just call it stiffness matrix, and delta is basically unknown primary variables vector, which can be called displacement vector, and F is the right hand side force vector, or it is just called right hand side vector. So we do that, and then after that we apply the boundary conditions. So boundary conditions properly can be applied, and there are some terms like eta 2 etc. in that relation. We told you about eta 2 in that relation, it was there. Just you saw that here. This was a relation of eta 2, say something, when we discussed about this one, about relations, that yes, in that we discussed what are the type of equations, and we discussed that there is a constitutive relation like this. So you are getting some eta 2. Now suppose epsilon dot EQ is very small, then eta 2 will become very high. Is it not? If epsilon dot EQ is 0, it becomes infinite. We don't want that type of situation. So we limit that. In numerical methods you have to do such type of things, that although theoretically if epsilon dot EQ is very small, eta 2 must be very large, but you say no, I will not allow it to go beyond 1400. And then you solve these non-linear equations in iterative way till it converges within 1% between two successive iterations. And then after you have find out everything, then you find out the derivative components, and then you find out epsilon dot equivalent Q is equal to 2 by 3. Here I have used index notation, that epsilon dot ij means I varies from 1 to 3 in 3-dimensional problem, j is changing from 1 to 3, but each component, since I and j are occurring twice, so all the terms are summed. That means epsilon 1 square plus epsilon 2 square, epsilon 1 square, like that we add. So that is summation convention we have used, and we find out equivalent strain, and then after that we put some criteria that if equivalent strain is very small, say it is 1% of the maximum strain rate, then that portion can be considered as the boundary of the plastic and rigid zone. So like that we estimate the primary shear deformation zone, and its width we can find out. Okay, so we do that this way, and now what happens that here, now in this one, here if we find out gamma dot shear strain component engineering strain rate is given like this, 2 times epsilon dot 12 and average of primary shear deformation zone, that shear stress, and then after that equivalent strain rate is also defined like this in this function 3 by 2 sigma dash ij, and this is a square root of that. Then we put all these things, and then after that we can estimate the shear zone, etc. So that means that mathematics I am skipping, but you can see that here some results that we took this data. Density rho is 7860, sigma y is given, m is this is a, and this is some exponent used in that model. This is not the m of that friction factor. This is something that in this constitutive relation, and we mesh the region like this, and then after that we use the cutting velocity, feed and rake angle we have taken in one way like this, and here we use 3% cutoff criteria, that primary shear deformation zone boundary is taken at that point in which the shear stress is about not the shear stress but the strain is 3% of the maximum strain. So by that we estimate the shear deformation zone, that means ds, what is the length of the ds, and ds came out to be like this, and experimental results from the literature provided this, and these are the predictions from the present model and experiment. So matching is quite good, and then we did some parametric study. We obtained that mean width of the primary shear deformation zone, that means the width of the shear zone, this one decreases with the cutting velocity, and it increases with feed, and then average shear strain rate increase in cutting velocity, the average shear strain rate increases expected, and it decreases with the feed, and average shear stress increases with the cutting velocity, which is in agreement with the experimental result. This is because of the shear, that means viscoplasticity effect. And when the cutting velocity is kept constant, then the average shear stress decreases linearly with the feed, and then we obtain the contours of the equivalent strain rate. These contours have been plotted here. So these contours are presented here. This is primary shear deformation zone. Suppose this one we have taken, this was I think experimental one, here that experimental one, and this we have got the contours here, that this one is say here you are getting equivalent strain rate 0.577 into 10 to the power 4, here it is this much, it is very high here, here it is somewhat here also it is high, then it is somewhat less here, and it is here 2.3 into 10 to the power 4, like that. So we have these values and we get the contour. That means contour meaning is that from here in this region, from here to here, one particular equivalent strain is there, here one particular strain is there, like that these contours are plotted. So this way that we can get some information about the cutting mechanics, but even if you do this analysis, usually it will take a lot of time. It is not that it is very fast, but it can give you all the insight about that where the strain rate may be high, where the stresses may be high, such type of things are done. Okay. So now these are the equivalent stresses, and they are it is observed that the maximum value of equivalent strain is 866 megapascal. 866 megapascal is this one, and then this is equivalent stress contour. That means here flow stress type of thing. Here you are getting less, but here you are getting more, and here also you are getting more. This one. So this is done. So this much I have told about that. I have given some exposure about the finite element model of metal cutting also. In more detail you can see from the published papers. Thank you very much.